So this is where we were. We were talking about how the shared memory has been filled, and now the sorting has to happen in the shared memory. And this is what is known as bitonic sort, which we will talk about. We haven't discussed the algorithm yet, but very briefly, depending on your bit pattern, you swap, you compare element with people who are different from you in a given bit position, right? So for example, in the first iteration, 0 and 1 will swap if necessary. 1, 2 and 3 will swap, 4 and 5 will swap, 6 and 7 will swap. And then you'll swap with people 2 distance away, then 4 distance away, and so on. And so, without getting too much into the details of the algorithm itself, you are making all the elements of the thread, all the threads of the block, going through this loop, and at each iteration of the loop, figuring out which is the bit at which my partner thread is different from me. Compute your partner thread's ID. So TID is your own ID. IXJ is your partner's ID, which is generated by taking an XOR with this loop variable j. And one of you is going to do the exchange, right? So you decide that between IXJ and TID, whoever is lower, right? So if your TID is less than your partner's, then you do this. Otherwise, the other guy will be figuring out you as your partner, and his result will be greater, so he won't be doing this. And then you, depending on the top level iterator k, you either swap if you are less than your partner, or swap if you are greater than your partner. Okay. And after everybody has done one swap, you have to sync, right? Because people are moving things around, right? And you want to make sure that all the warps of the block have moved things around, so that you can now go to the next level of iteration. So you can see who is two bits away from me, and whether I should be swapping with him or not. And once that is done, you come out of the loop and you put again your shared, all of the threads together have generated this sorted list, and you're going to figure out who puts which element from the shared memory into the global memory, and then you're done. Okay.
Should not be there sync threads after value is updated.
After this, there is an automatic sync thread because the kernel is done at this point. Right? After the kernel has come out, all of the blocks are done. So there is an implicit sync thread.
So suppose if you are doing this across blocks, then you need sync threads which are across blocks as well.
You would have to, or you figure out some other way to communicate across blocks. But there is no sync threads version for across blocks.
So what are the other?
One is you come out of the kernel. When you've come out of the kernel, all blocks are done. So you've synced. Other is you can put in some memory location whether this block has modified its data or not. And we can say every block gets one chunk of memory where it says, I have done my part A. Okay, then I see everybody has done their part A. I go to do part B. And that's where you would want to do voting within your warp, right? Because once you have done, your block has done your bit, you're waiting whether other blocks have done their bits. I'll in fact give you another example of something very similar. If every block has done their bit, then I need to take all the blocks results and see if everybody has done their bit, right? And so all the threads of my block will read the data for every block and do a voting. Right? If all is one, then all is well. All right, so let's continue the discussion that we were beginning to have about synchronization with reference to memory. Okay. What is the consistency model that the memory is providing? Now you know what the hardware does. What is that consistency model? So within a block, it's weak, right? Because you can say this is a flush, and then things before the flush and after the flush are ordered. Across the blocks, really no consistency, right?
Essentially a flush
At the end of a kernel, right? But not within. So you can think of that as one kind of weak, where you say that there's absolutely no guarantees anywhere except at the end of the kernel. But it doesn't count as weak because you don't have a function call that says now we are at the end of the kernel. Right? The system controls it. And of course you can't proceed in the same context beyond that because the kernel is done at that point. There is a bit of guarantee in that whenever people write things to memory, at the memory level there is consistency in that transactions are not mixed with each other. So memory is seeing a stream of transactions from different multiprocessors, different processors within the multiprocessors, and it is going to either discard some of those requests or fully perform those requests. It's not going to do part performance of any request. Okay, and it's not going to mix. It's not going to take your address and your data and write it at that position. Right? Either it's taking your address and your data, or your address and your data, and writing it at the right place. So that is the hardware level of consistency. Without that, there is no hope. Right? But beyond that, you can do some things at the software level. And for memories, there are these fences that are provided. Which, there is something called a thread fence for a block. Right? It is essentially a weaker kind of barrier. It's not quite a barrier, right? Because not all threads come and stop here. But when you call this method thread fence block, you're guaranteed that anybody who has called this thread fence block in your block is going to see the following behavior. Everything that they did before the thread fence block is visible to everybody in the block after the thread fence block. Okay, so if you wrote something and you have gone past the thread fence block, that means I don't know whether the other person has come to the thread fence block or not. But if they do, they cannot not see what I wrote. Anything I wrote before thread fence block is in the memory, guaranteed. Unless somebody overwrote it, that's a synchronization issue. But
all threads should call this function.
All
threads in the block or a single thread can call.
No, all threads in the clock in a block who need it would call it.
For everyone to call this simultaneously.
No, this is not a barrier.
Just a flush.
It is a flush. Yeah, it is a blocking flush. Right? When you come out of this flush, you know that it has reached memory. It's not just in the process of reaching the memory. And there is thread fence, which is across blocks. Right? When I call thread fence, I am ensuring that anybody else running in the same program, in the same kernel, is going to see this data after I have proceeded beyond the thread fence. Okay? And then there is thread fence system, which makes it visible to the host also. Right? So if I have proceeded beyond a thread fence system, the host will see this data. Are there any questions? And thread fence system is only on 2.x. The other two are available in the earlier versions also.
What can you say about the memory consistency within a warp?
Within a warp. Within a warp is essentially like thread fence. Rather sync threads, right?
Is it sort of processor consistency?
In the sense, if we have a sequence of thread fences called,
It is, I think, stronger. It is definitely processor consistent, but I'm thinking it's even stronger than that. Because you know precisely the instant where all of these calls were made. Right? So you can actually order them. You can make them sequentially consistent.
But if you make them sequentially consistent, then this is scheduling of warp. They also need some timestamp, but they don't.
Scheduling of work.
Is scheduling of threads inside a warp. I mean, they just reach the shared memory location at any time. So how do you say that you can make some warp?
Yeah, actually, you are right. What happens is, if you're doing it depends on the type of access. If your warp is writing ints, then it is sequentially consistent. Because, in fact, yeah, even for warp, half warp definitely, but even for warp, it's sequentially consistent because a half warp's entire read is going to happen in one shot or write, whatever. It's going to go to the memory as a single transaction. And two half warps, because you know exactly what happened after which, also get fully ordered. So each half warp's entire memory transaction goes in one order. If it is something bigger than an int, you're reading say 8 bytes per element, then no, even that can be done in one transaction, but something much bigger that cannot be handled in one transaction, then it's going to get partitioned into multiple memory transactions. But even that actually is deterministic. That algorithm is consistent. Hardware every time makes the same decision, and it is public. So as a programmer, you also know what is the order among the different read and write calls to the memory. And because they are going to go through the same cache also, there is going to be absolutely no reordering anywhere. So that is not true. So it is definitely sequentially consistent now that I think about it on 1.x. 2.x has made it, in order to make it more general, has caused some consistency.
You even don't need many sync threads, and things that you don't even need sync threads many times, which you need into 1.x program. So many things are not that they don't care about synchronization that.
No, you don't need sync threads all the time, even in 1.x. It depends on whether you are syncing across warps or not.
But many sync threads, like just after reading the data, you need sync threads in some programming models in 1.x. In 2.x, you don't care about. That also has been removed.
No, I don't know exactly what you're referring to, but sync threads is essentially ensuring that all the blocks, all of the warps of the block have come to this position. And Fermi does nothing about it. Right? All the blocks are executing in their own order. And it's possible that this block this warp of the block has reached instruction number 10, where that warp of the same block is at instruction number 1. So unless you sync, how are you going to get to the same spot?
In programming, it's like reductions and all. After reading the data, you need some sync thread.
It depends, right? If there are multiple warps of the block reading data, just like in our example just we saw, we needed to sync thread, and that is not going to be removed for 2.x, because every warp in the block has to have finished its read before you can proceed further. So if you as a warp have to depend on some other warp to have finished something before you can proceed further, then you have to wait for them. You have to sync with them. And 1.x or 2.x, both of them will have to do the same thing. Okay. So back to what we were discussing. In 1.x, because of no reordering in the cache, there was sequential consistency. In 2.x, because they are letting cache lines be evicted in their own order, it is weak consistency. You can still make sure that you get flushed, but you just by writing, it's not going to get there. You can use volatile. If you only use volatile, then you get back to having a sequential consistency. Okay, so let's look at that piece of code, which uses very small font size and also thread fence. So let's begin with where we were. We were talking about memory fences, right? So there was synchronization where you said explicit synchronization between different threads of the block, and that is really all the synchronization that is provided among CUDA threads. Between kernels, there is some synchronization, right? So one kernel clearly comes before another kernel, and unless you want them to run concurrently, they will run in sequence. And so everything that has happened in the previous kernel will finish before the next kernel begins, most of the time, which means that unless you want otherwise. There are then, so that's the synchronization side of the story. The other side is indirect synchronization, which is making sure that the things that you have written in memory are actually visible. Okay, so thread fence is for that, and this is something that you would see even in multi-core CPU. Thread fences are there. You may not directly use them, or you may not typically have functions that in turn call the memory thread fence functions, or the primitives that the hardware provides. But the function calls like lock, mutex, etc. will typically use those things under the hood. All right, so the thread fence we talked about is on the block, which says that I've written something and everybody in the block now knows about it. I've written something and everybody on the thread, on the device knows about it. And I've written something and even the system knows about it. Right? System knows about it as long as what I'm writing to is also visible using mapped memory on both sides. All right, so this is where we were talking about that code, which I have now split into 2 slides, but it still seems a little small, but I think it's readable now, right? So it's reduce. You have a block which takes the elements that are within the purview of the block, the responsibility of the block, adds it together. And then multiple blocks are adding the elements within their block, and then somehow they need, or one of them or multiple of them need to then take these partial sums that each block is producing and find the grand sum, okay? Find the total sum. And so some of those details are abstracted over here. You begin by a block, so this is the kernel, right? So for a block, they are sharing this data somehow. They are computing the partial sum using whatever technique that they may have used, which takes the input, which is the list of elements, and generates the sum for this block. Okay, partial sum is for the given block. Would you declare it as float partial sum for a given block? Is that declaration?
So the array is also float.
Oh, no. I meant, is it shared, device, any qualifier necessary? Not the type. Right now, who owns it? Each thread has its own partial sum, okay? Now, if I am thread index 0, hopefully everybody is reaching the same partial sum. In the shared memory, everybody is doing this log reduction, right? So everybody has their own partial sum. And one data needs to be produced for this entire block. So we'll say one of the threads, thread 0, takes the responsibility, and it writes its partial sum, which we are going to assume is the same on every thread, which is the sum of the block. Okay. So if thread index is 0, then you take your partial sum, put it in your block ID, right? So there is a result which stores the partial result for each block, result array, and there is one slot reserved for every block. You figure out your block ID, you put, that is your slot, you put your partial sum there. Fine, nothing fancy happening so far. Then why do you need a thread fence? Although comment there says
It's being written in the global memory. So once we write it, we should be sure that once we cross that particular instruction, everybody gets to see what we just wrote.
right.
True sharing.
Sorry?
Anything to do with the sharing or sharing?
Not quite.
Because when you're updating one, it will not. It is also doing caching.
So this is, you're writing only once for the block. Right? One member of the block is representing the block, is writing for the block. Right? And that item may be cached here, and there may be sharing, which means it's also cached over there for some other block, which may or may not be running on the same multiprocessor. So there may be sharing, but that false sharing has more to do with efficiency. So let's proceed what is going to happen. So let's in fact first talk about what should happen. Everybody figures out their partial sum, and then somebody is going to add the partial sum. You need to make sure when that somebody is going to add the partial sums, or a group of threads are going to add the partial sum, is that everybody has figured out their partial sum and written it, right? Because blocks are independent of each other, they are not synchronized. So your block is done and you have written your partial sum. It doesn't say anything about where the other blocks are. They may not even have begun yet. You ensure here that whatever you have written is going to go into the memory beyond this point. Right? So anybody else who reads it, who is going to read it? Who is going to now combine the elements within the result array? Whoever reads it, it may not be you. If you read it, you know you're going to get it without even thread fence. But if somebody else reads it, you need to have thread fence here, so that they can get the updated or the correct value, the value that you actually wrote here. And it's not sitting in cache somewhere. Okay. And then there is this, how do you know that everybody has written? So you can go to the next phase and add the partial sums. In this case, there is a counter, and everybody who has written atomically increments that counter.
Shouldn't it be block div.x?
Which one?
Atomic increment. Every thread of a given block increments its own blocks count, right?
No. There is a single count that says how many blocks have done. You know how many blocks are working on this grand problem, right? And so you say, I am also done. Somebody else says, I am also done. So you're incrementing by one a global counter. Okay? And those of you who did something of this sort should know what this atomic ink is doing. Why is there a griddim.x there? It's incrementing by one. This variable called count, which is in the global memory. None of you used atomic?
That's the maximum.
So it shouldn't be. So I found a comment that it shouldn't be used because it serializes in some sense.
Atomic serializes
It serializes.
at a very short interval.
It loses the logs computations.
Yes. Right. But sometimes you have no choice. Here you have a choice. If you weren't doing atomic, what would you do? What is one of the things or a few of the things you might do?
Create an array. Right.
Parallel sum.
Return the kernel.
Yeah.
So return the kernel is one, but that has its overhead, right? Now another kernel will have to start and do something. What was the other suggestion?
Like your result, you are storing the partial in the result array. You can create one more array and that ID block.
So you enable your bit. You say my bit is done, but how do you know that all bits are done? When and who will do that?
That can run on.
Busy wait. One of the blocks job is to figure out whether all the bits are one. That can be done, but it's a little expensive. So here there are all these computing options, and depending on how slow the atomic is, it may or may not be faster than, say, keeping a block doing nothing but checking if all the bits are one, right? Okay, so the second parameter here says that's the maximum that you can increment it to. Okay.
Atomic is not a single instruction function. It's like
It will map to a single PTX instruction, which is supported in the hardware. It effectively means you read something, you add something to it, and you put the value back.
so there are two things. It is done atomically, and second, it is done in single instruction.
Yes.
So it always increments by one, or
This instruction always increments by one, and there is a max. It says don't go above it. In fact, it resets it to 0 when you reach there. So you can have a recycle instruction. Okay, so you've incremented your value, and somebody needs to check if that value has become the full size of the grid, right? How many blocks you had started with. So everybody does that. Wow, once you are done with your partial sum, you can go check if that thing is, that counter has reached max. Right? So everybody in parallel is figuring out, is everybody else done? Once they are done. Okay, the question?
so why -1?
Because it will never reach that value, it has to go to 0. Right? You start with 0 and you keep incrementing, and you will
griddim.x number of blocks.
griddim.x is the number of blocks.
So
Semantically,
It starts from 0, the numbering starts from
agreed, but the count
the value is the
has to
Value
be
is
griddim.x, right?
The value returned is the old value. When you do atomic ink, you get the old value back, right? Not the value you are incrementing to. So everybody is figuring out again, it's a local, this variable is local to this block, right? It's in shared. And so we figured out that this variable has reached, and all these blocks are figuring out whether this is done, right? Once you've checked that, you come out. So blocks who reach there early are not going to go back and check in this case. Right? They are not busy waiting. There's no loop here. It says if thread index is 0, which means I am representing my block, I'm going to write my result. I'm going to check if I'm going to increment that count. I'm going to check if that count was already at n-1, means n-1 other people had written it before me. And I'm going to set my variable to is the last block done. So how many people will see this variable to be true? One thread of one block, right? The block that happens to get the last access to the atomic operation. Then we do a sync threads. Why is that necessary?
All threads of
Yeah, but what does it mean?
Only after thread 0 is updated, sir.
All threads of the block that found that it was the last block are going to in parallel sum the partial sums. Okay, so they're all going to become active now and start participating in summing it. Right? But the other threads, if you look back here, didn't go through this if condition, right? So they immediately went to the end. Should they wait for this guy to check and update whether this is the block to do the partial sum, the final sum? Of course they should, right? So they're waiting there until this thread 0 comes along and says, yes, we are the last. Our variable, which is shared across all of us, is set to true, meaning this is the last block to come. And let's now find the final sum. Okay, so now everybody checks, is last block done? And if this is the block that is the last block, then all threads of this block will see this to be true. And now they are going to go figure out the sum in this partial result array. And then if I am thread 0 of this block, I'm going to write the resulting value, just like the previous, when I was doing within a block. I'm going to write the resulting value, total sum, into the result. Okay, so this demonstrates that where I think, I at least hope that sync threads was obvious. You had to wait there to figure out whether or not you were responsible for doing the remaining work. And the thread fence. Whenever you want other blocks to read what you have written, in this case other blocks are somewhere on the device, but what you have written is in the global memory and accessible to other blocks, then you make sure that thread fence is done so that it doesn't sit stale in your cache somewhere. Okay, any questions on memory synchronization? All right. So finally, let's also talk about how to increase the concurrency by using streams when we want to have multiple kernels running in parallel, or having memory transfers going on for one kernel when the kernel, some other kernel is actually executing, and so on and so forth. So the idea of stream is straightforward. You break down your computation into different sequences. Each still is sequential from the host's point of view. But these different sequences, or streams so to speak, are concurrent. Right? They're not independent of each other because there are some restrictions on when a given stream's operation can run versus other streams. In fact, we'll go through an example to see those kinds of restrictions. And I'll also show you the example of how a stream is run by code, so you don't need to worry about the exact sequence that is being demonstrated in this slide. However, one thing to note is that there always are streams. Right? When you're not explicitly using a stream, you're saying everything is going to stream 0. All right? So from host's point of view, there is a sequential stream called stream 0. And when you don't specify a stream, or your operations are not explicitly targeted towards a stream, then they are targeted towards stream 0. Okay, and everything on stream 0 is sequential. So when stream 0 is running, no other stream is running. Other streams must wait for stream 0 to finish. And so if you actually want concurrency, or in places where you want concurrency, you will not be sending things to stream 0. You can also query a few things about the stream. You also have this notion of events. So you can say whether this stream has reached a certain point, and so on and so forth. But let's look at the example. So you would declare some variable of type CUDA stream and allocate a few streams. Okay, CUDA stream create as many streams as you like. Again, there's some maximum limit. In this case, a page log memory on the host is being allocated, right, by using CUDA malloc host of certain size. Then you do in a loop what you would normally do in a stream. In a stream, what do? You say memcopy some memory from host to device, run this kernel, get the result back. Okay, that triple has been put in a loop. So now you're saying for int equal to 0 to 2, which is 0 and 1, you do this thing, but so in CUDA memcopy async, the last parameter says which is the stream for which this CUDA operation holds, okay, the target. And so the first memcopy kernel memcopy back is going to stream 0, not the sequential stream, not the stream ID 0, whatever is in your stream variable here, stream array 0, which will most certainly not be 0. And then do the same sequence for stream 1. And later, if you wish, you can destroy the streams. Can something go wrong? In this case, probably nothing goes wrong, because if you look at what the memory areas they are copying is, it's totally disjoint. Right? First guy says, my left half, do the kernel on that part, then get the left half back. Second one in the meantime is doing the same thing on the right half, and hopefully there is no dependency on left and right half. You can't know. That depends on the kernel.
Will it actually be asynchronous?
Sorry?
Will it actually be asynchronous? Because it should block at open for memcopy to complete.
So what is going to happen is that two memcopies, as long as, so the older devices, everything is synchronous. Okay, so memcopies and kernel launches are all going to happen independently, which is 1.0. I think 1.1 onwards, memcopy and kernels can overlap, but under more gradually less restrictive set of conditions. So for mostly any CUDA device you find today, the first 2 copies can happen in parallel. Okay, so your left half going into the CUDA device and right half going into the CUDA device can happen in parallel. Will it happen in parallel here? Can it happen in parallel here? What have you structured it as? You have said copy the left half, then launch the kernel for the left half, then bring the results back, now copy the right half. Okay?
All these are async calls.
It may be async calls, right? Which means that you return. Fine. But can you, as a system implementer, allow the second copy to device to proceed?
Because that's on a different stream, process streams independent.
That's the thing. That's why I said they're not independent. You cannot assume they're independent. You could, right? Then the entire responsibility goes to the programmer to make sure that whatever interactions are happening within stream are fully protected by mutual exclusion or some synchronization method. So go ahead.
What do you mean by that? As in, are the two streams not semantically independent?
No. They are concurrent, which means it's more of a feature that you as a programmer can use to speed your computations up. Right? You can have multiple kernels running so that there are enough threads available for every SM to have some work to run at every clock. That's ultimately what you would like.
So still again there will be set of kernels there in memory, but they'll be scheduled on the GPU. That's how it's right. It's not like they've been broken and one half will be running, the one kernel next to is in another half. It is still scheduling between the two.
There is scheduling, yes. So kernels,
It's not exact concurrency.
it can be, right? It can be that one kernel is running
On a set of
on the first 3 SMs and the second kernel at the same time is running on the 4th SM.
So how will that control? How do we control that?
Streams.
So how does the stream help you to tell which are the SM?
It doesn't help you to tell, right? If it is possible to run it, it can be run. The system will run it. Possible meaning there are these dependencies, there are a few dependencies that need to be respected. If you respect those and there is device available on which new blocks can be scheduled, they'll be scheduled.
But if they are working on entirely different sets, then we can assume that we will be having correct result. Otherwise, global memory is same for all.
Global memory is the same, yeah.
So there may be some.
So if your kernels, the two kernels you have launched, interfere with each other, then you can get in trouble.
Single call, we say that it behaves as in static memory, but in this case, it may not be behaving the same.
Yes, precisely. It can happen. And when that means you're sharing across two different concurrent kernel calls, think of it on the CPU side, two different threads sharing a shared memory.
Just like you're creating more work so that the GPU is all the time working.
GPU is yes.
Just like creating more blocks, creating more threads per block. That's how it is.
Yes.
You want to do more threads because you want the GPU to be always be occupied.
Always be occupied. Yeah.
And if the thread is not good enough, you have more blocks, and now you are seeing more kernels.
More kernels, right? You want to do something independent at the same time, or even if dependent, as long as you make sure that the sharing is properly controlled, you can run it. Right? So what CUDA will not allow you to do is run a new kernel where the old kernel's results are not back from the memory yet. Okay. And so in this old kernel's result, which has been ordered earlier by your program order.
In the same stream.
No, there is a host program order. The host program order will be respected by certain aspects of the stream. Okay, one of them is that if the data hasn't come back, then any kernel launch or in fact any CUDA copy that is host ordered later cannot appear first. Okay, so that defeats this entire concurrency.
You can always do this in a hash flag or empty parallel for as well. In which case, the notion of, you should different.
In different threads. Yeah, you can do it in different host threads, then this dependency is lost. Yes. But if you wanted this dependency, you'd keep it there. If you completely don't want this dependency, you can put it in two different hosts. Which, by the way, didn't work very well. Implementation issues for older versions of CUDA, I believe. Do you have any?
But we did it through different threads.
Which version of since the beginning? Okay. I thought in CUDA until 2.0 or even 1.
We did not try
Something.
before.
Oh, you didn't try it before that. Okay. Yeah. Before that, there was some issue with multiple host threads running in parallel, which is not there anymore. So that's one way. The other would be you put the three statements in their own loops. Right? What will that do? That will say the two mem copies are after each other. The two kernel launches are after each other. And then the two results back are after each other. So now the two mem copies can happen in parallel. The kernel launches can be launched in parallel. And the results can be copied back in parallel. There is a bit of a restriction still that the copying cannot begin until the last block of the kernels have been launched, have actually been sent. Okay. So that slightly reduces the amount of concurrency that you would otherwise get. Earlier blocks launching can begin. Launching is not an atomic operation, right? You say, here is some more work, here is some more work, and the GPU will at some point say, I can only take on that much work right now. And so if you have a big kernel launch, which has lots of blocks, then until the last block is launched, you cannot start reading the results coming out. Okay, so that's a restriction.
No, but you can use that because you are not sure whether the device memory is ready with the results.
That's the reason.
But why is it like before the last block is, just after the last blocks are launched and not when they're finished?
For a different stream, right? So you cannot start copying back stream 1's result back until zero's last block has been launched. Okay. Of course, within your own stream, you have to do that. All right. There are also, as we just discussed, synchronization allowed, or procedure for synchronization. There is a CUDA thread synchronize, which is, it's more like fence. It has the semantics very similar to fence, where you say, when I say CUDA thread synchronize, then all the preceding streams or commands that I have issued to preceding streams. This is again from the point of view of a single host thread. Okay, when you have multiple threads, then they are concurrent, they are independent of each other. Within a thread, all the stream calls you have made have to be finished. Stream synchronize is a version of thread synchronize, except it takes a parameter which says all the calls of that particular stream have to be finished. Okay, and then there is a CUDA stream wait event, which takes a stream and a given event, and it says all the calls for that stream up to that event have to be finished. And then there is a query about the progress of streams. Right? You have forked off many streams from your thread, and you want to know how far they have reached. So then you can query for the stream, assuming the streams are marking either counters which exist or events which tell you how to monitor the streams, or how to read the progress that you're making. Okay, so that's as much as we are going to talk about the features of CUDA. I still want to spend a little bit of time talking about the performance issues, right? How many threads and how to read memory and all that. Any questions? And I'm going to stop here.